Okay, thank you for coming, everyone. My name is Joo-hoon Kang, an assistant professor of material science and engineering at SKKU. Today, I'm gonna start with Professor Mark Hersam at Northwestern University. Professor Hersam is the Walter P. Murphy Professor of Material Science and Engineering and Director of the Materials Research Center at Northwestern University. And he also holds faculty appointments in the Department of Chemistry, Applied Physics, Medicine, and Electrical Engineering. He earned his BS in Electrical Engineering from the University of Illinois at Urbana-Champaign, or UIUC, and his Master in Physics from the University of University of Cambridge, and his PhD in Electrical Engineering from UIUC again in 2000. And his research interests include nanomaterials, nanomanufacturing, nanoelectronics, scanning probe microscope, renewable energy, and quantum information science. Dr. Hersam has received several honors, including the Presidential Early Career Award for Scientists and Engineers, TMS Robert Lansing Howard Award, AVS Peter Mark Award, MRS Outstanding Young Investigator, US Science Envoy, MacArthur Award, and AVS Medard Welch Award, and then a Teacher of the Year Award. And I believe that you have another award just added today from the UCLA, like a triple A AFM Stoddart Award. Congratulations. And then Dr. Hersam is an elected member of the National Academy of Inventors, and he has founded two companies, NanoIntegris and Volexion, which are commercial suppliers of nanoelectronic and battery materials, respectively. And Dr. Hersam is a fellow of MRS, ACS, ABS, APS, AAAS, SPIE, and the IEEE, and also serves as an associate editor of ACS Nano. I'm very happy to introduce Professor Mark Hersam. His talk entitled Boron in the 2D Limit, Borofane, and Beyond. Please welcome Professor Hersam.
All right, thank you very much, Joo-hoon, for the kind introduction. I'm gonna quickly get the presentation set up here. It's a great honor to give this talk, especially because Joo-hoon is an alum of my research group. One of my most successful PhD students. I'm very proud of everything that he did in my lab, and he's now doing at SKKU. Today, though, let me jump right in since we have limited time and talk about work that we've been doing in the area of boron, particularly in the 2D limit. And I'll introduce what I mean by borofane, and related topics today. Before I jump in, though, let's go through an outline of the talk. I'm going to begin by discussing boron, how we synthesize it, and the atomic structure of borofane and its polymorphs. I'll then move into how we integrate borofane into both lateral and vertical heterostructures with materials like graphene and graphene nanoribbons. And then, if time permits, talk about our latest work where we're trying to now move borofane out of the ultra-high vacuum environment using schemes such as passivation with hydrogen. And since there is limited time today, I do encourage members of the audience who are interested in more background information to take a look at these review articles listed here, which will provide a lot of background information. Let's now jump in and talk about how we synthesize borofane. Before I do that, let me first introduce you to bulk elemental boron. This is a topic which may or may not be familiar to some of you. And what I want to stress is that boron is a valence 3 element, and as a result, elemental boron struggles to satisfy the octet rule, in contrast to an element like carbon. And as a result, bulk elemental boron is highly polymorphic. It has diverse building blocks, including B12 icosahedra, smaller boron clusters, and larger cages. And ultimately, bulk boron is a balance between conventional 2-center 2-electron bonds and less conventional 3-center 2-electron bonds, also referred to as banana bonds. I will note, though, that there are some compounds, such as magnesium diboride, wherein the boron does form graphene-like sheets, but I'll note that these are tightly bound within the solid, and as a result, you can't simply exfoliate boraphenene from boron or any known boron compound. This is in stark contrast to materials like graphene, which are easily exfoliated from graphite. And as a result, it stands to reason that if you wanted to realize a 2D phase of boron, you would not go from the top down, but rather from the bottom up. And as a result, it's worthwhile to look at boron nanoclusters to see how they could potentially be arranged into 2D lattices. These are typically formed via laser ablation and vacuum. And small planar structures have been observed, either based on buckled triangular lattices of hexagonal pyramids, or as these get larger, you tend to find structures that adopt vacancy structures, or these so-called hollow hexagons in an otherwise triangular lattice. I'll note that these hollow polygons also show up in the larger non-planar boron fullerene clusters. And as a result, if we imagine going from the bottom up, there are several possible structures of 2D boron. You could imagine those icosahedral B12 clusters forming some sort of 2D lattice. You could imagine the buckled triangular lattice of hexagonal pyramids. You could also imagine taking a BAB fullerene, unrolling it, and then forming that into an extended 2D lattice. And that would be a triangular lattice with a periodic array of hollow hexagons or vacancy structures. And if you calculate the stability of such structures, you find that it depends upon the number and arrangement of those vacancies. And it turns out that the energy is minimized if you have 1/6 or 1/5 of the boron atoms missing from the triangular lattice. And this is further lowered in energy if you were to grow the material on a noble metal such as silver. And if you were able to realize such a structure, there are many properties that have been predicted. This should be a 2D metal with confined and anisotropic plasmons. It should have high optical transparency and therefore be useful for transparent conductors. It should have high mechanical flexibility and stretchability. And since boron is one of the lightest elements in the periodic table, it's predicted to have relatively high temperature superconductivity, analogous to magnesium diboride. And as a result, these sets of properties are of interest and therefore help motivate the realization of boron in the 2D limit. And so the way that we ended up getting there was to go to an ultra-high vacuum environment, form an atomically clean and atomically flat silver 111 substrate, and then evaporate atomic boron onto that substrate. And at suitable substrate temperatures, you do form two-dimensional phases of boron. And as you can see in these two STM images, the exact atomic structure you get depends upon the growth conditions. And here's at least two possibilities. One we'll call the R phase because the unit cell appears to be rectangular, and the other the D phase since the unit cell appears to be a diamond-like shape. I will note though that from UHV STM alone, you cannot uniquely determine the atomic structure since you have a convolution of electronic and topographic information in an STM image. And as a result, you need to use other methods, and one that was particularly useful was synchrotron X-ray photoelectron spectroscopy. And this allows you now to reveal some of the chemical bonding that's occurring in these 2D boron layers. And in particular, for the so-called R phase that I introduced in the last slide, what you can see in the boron 1s spectrum are three distinct peaks, which suggests that there's three distinct coordination numbers for boron in this structure. And if you take possible rectangular unit cell structures of 2D boron and consider which of those can have three different coordination numbers for boron, you learn that there's only one plausible possibility, and that is the so-called V16 structure here, wherein you have 1/6 of the boron atoms missing in the otherwise triangular lattice. In contrast, for the D phase, you see two distinct peaks. This suggests only two coordination numbers, and among the plausible 2D boron layers that have a diamond-shaped unit cell and only two coordination numbers, you find that the V1/5 structure is the one that meets those conditions. And that's where we have 1/5 of boron atoms missing in the triangular lattice. Now that's quite compelling, but ultimately seeing is believing. And so in subsequent work, what we did is utilize a refined scanning probe method, namely functionalizing our scanning probe tips with carbon monoxide. And that yielded even higher and more definitive resolution of these hollow hexagons that we deduced from the X-ray photoelectron spectroscopy. The way that this works is you take your borafine on silver structure, you leak carbon monoxide into your chamber, and it absorbs selectively on the silver. You pick it up with your STM tip and you confirm it's present with inelastic electron tunneling spectroscopy. And if you then go and you re-image your borafine with the CO on the tip apex, you can see that you get an enhanced resolution in CO STM imaging. But even more compellingly, if you move into non-contact AFM mode, which is less sensitive to electronic structure than STM, you now see in real space these hollow hexagon structures that we deduce from X-ray photoelectron spectroscopy. And if you simulate, in this case, the V1/5 structure, you see very nice agreement with experiment. This also allows you to interpret the STM image, and what you can see is that the protrusions in CO STM correlate with the hollow hexagons in the real topographic structure. And therefore, you can utilize CO STM to deduce other possible arrangements of boron atoms in a 2D lattice. And indeed, over the subsequent years of study, we're able to map out several different borafine phases, the V1/6 and V1/5. We also found V1/6 and V1/5 phases that were rotated with respect to the silver lattice. You can also find additional incommensurate phases, such as these that are rotated by 22 degrees with respect to the silver. And it's also possible to form superlattices of different borafine polymorphs, as we see here, where we have mixtures of the V1/6 and V1/5 structure. And since those form more extended superlattice structures, it allows you to realize additional phases, in this case, the so-called V4/21 structure with a 22-degree rotation with respect to the silver lattice. The bottom line is that borafine is almost endlessly interesting in that it's highly polymorphic like the bulk, and as a result, it doesn't constitute one material, but rather a family of materials. Okay, so let me move on and talk about how we can now take these borafine materials and integrate them into more complicated lateral and vertical heterostructures. The first one we went after was a borafine graphene heterostructure, and our strategy was to realize that on the same silver 111 substrate that we grow borafine, you can also grow graphene. And you do it in a very similar way by, in this case, evaporating atomic carbon onto silver 111 at a suitable growth temperature. And it turns out that to grow graphene, you have to go to a higher temperature than borafine, and that temperature is about 700 degrees C. And nowadays, after refining this growth over several years, we can get almost perfect graphene with very few atomic defects, as you can see in this image here. The idea then is to grow a submonolayer of graphene and then switch over to the atomic boron source and grow atomic to the boron subsequently. This you can imagine nucleating either on the fresh silver if you originally had a submonolayer coverage of graphene. And if that were to occur, you can imagine that borafine growing until it hits the graphene and you form a lateral heterostructure in that case. You could also imagine the boron intercalating underneath graphene. And indeed, in this image here, you can see individual boron atoms intercalated underneath the graphene, and that perturbs the electronic structure of the overlaid graphene. And that's what these dark protrusions are on the graphene in this case. And if that boron, which is intercalated under the graphene, got dense enough, it could begin to nucleate into borafine itself and thereby form a graphene-borafine heterostructure vertically, where the boron is underneath the graphene, even though the boron was grown secondly. And all three of those cases are seen in this one STM image. If you then zoom in and look at particular cases, such as the graphene-borafine vertical heterostructure, you learn that based upon the imaging conditions, you can either reveal the graphene lattice, which is clearly apparent in apparent barrier height imaging, whereas if you tune into other imaging modes, such as more conventional STM imaging, you can reveal the borafine lattice. And because you can get these images in the same region, you can use methods like fast Fourier transform analysis to determine the relative orientation of those two layers in the vertical heterostructure. You can also look at the lateral heterostructure. We find that CO STM imaging most directly reveals the bonding in these lateral heterostructures, and it's quite interesting to me, at least, in that you can see on the graphene side, you have essentially perfect graphene lattice. On the borefin side, you also see that hollow hexagon structure I showed you before. And now you can inspect the hetero interface. And even though these materials are not lattice matched or even symmetry matched, you find that the distance over which you go from perfect graphene to perfect graphene is literally on the order of 1 nanometer. So over a couple of lattice constants, you transition from one to the other. And this is, I think, somewhat surprising. Normally, when you have a lattice mismatched system, it requires many lattice constants before you can return to the pristine atomic structure. And I think the fact that it's so abrupt, despite the poor lattice matching, is further indicative of the polymorphic nature of boron. It really has a hard time satisfying the octet rule and will contort itself in all sorts of unusual geometries in order to do its best to achieve that condition. In addition, we can use methods like scanning tunneling spectroscopy to look at the electronic density of states across the hetero interface. And as you may expect from this relatively abrupt atomic structure transition, you also see a relatively abrupt electronic transition, wherein you go from graphene to borefin electronic structure over the length scale of about 0.5 nanometers. And this is also unusual if you think about other metal semiconductor, or in this case, metal zero bandgap semiconductor heterogenesis. You often see a lot of charge transfer and other effects that lead to depletion regions and other electronic perturbations over much longer length scales than you see with borefin. The other system that we've gone after is a true boron semiconductor heterostructure, taking advantage of the fact that it is metallic. And in particular, we went after graphene nanoribbons. The way that we did this was to use a molecular precursor, in this case, dibromo p-terphenyl, which is known at elevated temperatures on silver 111 to be transitioned into graphene nanoribbons. And indeed, when you deposit DBTP onto silver 111, you see nicely ordered monolayers. Perhaps more interestingly, if you deposit DBTP onto a submonolar coverage of borefin on silver 111, you find that the molecules adsorb selectively on the silver. And at relatively modest annealing conditions of about 110 degrees C, you find that these molecules form relatively ordered structures, but are avoiding the borefin, which then suggests that if we go to higher temperatures to convert these into graphene nanoribbons, we would have a graphene nanoribbon borefin heterointerface forming spontaneously via the molecular self-assembly. And that is indeed the case. If you heat this up now to 300 degrees C, those molecular precursors now assemble into graphene nanoribbons. In this case, we get so-called 3 armchair graphene nanoribbons, also known as polyparaphenylene wires. These are semiconducting structures, and you can see that clearly in the electronic density states. And you'll note that they form a very sharp heterointerface with borefin. And again, if we now take scanning tunneling spectra across the heterointerface, we see over the length scale of less than 1 nanometer transition from the metallic borefin electronic structure to the semiconducting structure of the graphene nanoribbons. So again, we see this very abrupt electronic transition, not evidence for the more traditional Schottky-like depletion layers that are formed in conventional bulk semiconductor metal heterojunctions, and suggests that something special is happening here in the two-dimensional limit. Let me move on in the last few minutes to the final topic, and that is to now discuss our most recent efforts to move borefin out of ultra-high vacuum. Everything I've shown you thus far has been synthesized and characterized in UHV. And the idea that we had is one that was inspired from the old silicon literature. Silicon also is a material that's highly unstable out of a vacuum environment unless you passivate it with hydrogen. And so we thought that perhaps hydrogen could also be useful as a passivation layer for borefin. Indeed, the way that we do this is that we expose borefin to atomic hydrogen at room temperature, and it begins to decorate the surface with hydrogen add atoms. Converting borefin now into a hydrogenated borefin Or an analogy to hydrogenated graphene being called graphane, we'll refer to this as borane for short. But just like borane, there are many allotropes of borane. We've observed at least 8 distinct borane polymorphs. And I'll note that among them, the V1630 degree polymorph is the one that we can form with the highest coverage and the highest atomic purity. I'll further note that this hydrogenation is fully reversible. You can heat this up to 300 degrees C and reversibly convert back into borane. So this is a temporary passivation layer if you wish to remove it at some later point in time. As I noted, the dominant phase is V1630 degree borane phase, which we can for about 80% of the surface, and it forms a nicely ordered rectangular-like lattice. Which then begs the question, where are the hydrogen atoms? And if you take STM images and you compare them against simulations, you find that there's 2 plausible structures that are consistent with the STM data. They're both rectangular unit cells. One of them has only 1 hydrogen per unit cell, and the other one has 2 per unit cells. So we'll call that rectangular 1H and rectangular 2H. In both cases, you have the 3-center 2-electron or banana bond present. But in the rectangular 2H structure, you also have the 2-center 2-electron traditional boron hydrogen bonds present. And as a result, if we could come up with some spectroscopic means of identifying this 2-center 2-electron bond, then we would be able to conclude that the rectangular 2H is in fact the structure that we've realized. And so we did this with 2 different spectroscopic methods. The first is scanning tunneling spectroscopy, which gives us the electronic density of states. We see a very strong peak at about 1.2 electron volts. And in density functional theory, you see that the rectangular 2H structure also has a peak at that energy. But perhaps even more compellingly, we can look at the inelastic electron tunneling spectroscopy, this is the vibrational structure. And we see that the vibrational spectrum shows clear agreement with the rectangular 2H structure and not with the rectangular 1H structure. And to further verify that, we can deuterate the surface, and we find that this vibrational mode shifts in a very predictable manner, as you'd expect from traditional vibrational spectroscopy. And as a result, we can conclude that the rectangular 2H structure is that which we have achieved. But perhaps most importantly, from an application perspective, this hydrogenation allows borane now to be taken out of the ultra-high vacuum environment. To show you this, I'm first showing you is borane. If I take it out of UHV for 1 hour and look at it with either atomic force microscopy or X-ray photoelectron spectroscopy, you see very clear evidence of oxidation occurring. And that's this peak that you see at about 193 EV in XPS. Whereas for borane, if you take it out of vacuum for an hour and image it with XPS, you see no evidence of oxidation. After a day, you still see no evidence. Only after a week in ambient conditions, you begin to see a very weak oxidation occurring. And as a result, you have literally days now to encapsulate your borane with some other add layer. For example, you could use atomic layer deposition to grow alumina on this layer to encapsulate it to give you very long-term stability. And as a result, let me conclude there. I'm sure I'm out of time. I tried to make 3 points today. One is that multiple borane polymorphs in superlattices can be synthesized on silver 1-on-1 surfaces. You can also realize that electronic structures for both graphene and graphene nanoribbons. And hydrogenation, we believe, is now the pathway to getting this material out of UHV into ambient conditions, which is going to, we believe, accelerate its use in a wide variety of applications. With that, let me conclude by acknowledging my research group at Northwestern. I'm happy to report, at least last month before the Delta variant took over, that we could meet in person. So this is a very recent photo from our group. Also want to acknowledge all the funding agencies for supporting the work in our lab, and I'll be happy to take any questions.
Okay, thank you very much for your wonderful talk, Mark. And then we have just 1 minute, so let's take one question from the audience. Does anyone have any questions for Mark? I think no one have any questions yet. So I have a very quick question. It's kind of a general question. So I guess my question is that you just summarize your borofin and the borofane related works, and then in the last slide you mentioned that kind of a variety of applications based on the borofin and borofane things. Do you have any particular applications keep in mind based on these boron allotropes?
Yeah, so I think the short-term opportunity is to exploit its metallic character. And the fact that we see in heterostructures in STM that the electronic interface is so abrupt implies that you can really use it as an electrical contact to highly scaled devices. Whereas if we were to look at traditional metal bonding to a material like moly disulfide, you'd see a transition on the order of 10 nanometers, which means that you can't really make your device any smaller than that.
Right.
But for ultimate scaling, you need a metal contact, very abrupt electronic interface, and I think that's the opportunity for borofin in the near term. Longer term, things like its plasmonic properties, its predictive superconducting properties could be useful in other contexts, such as quantum information science.
Okay, thank you for your response. And then if there are no more questions, then let's thank Mark again for his nice talk.
Thank you.
Thank you very much, Mark. Okay, then let's move on to the next speaker, Dr. Herin Im from Seongkyungwan University. Dr. Im gonna talk about the chaotic organic inorganic phosphorant patterns for physical unclonable functions. Dr. Im, are you ready to talk?
Yeah, can you hear me?
Yes, we will.
Yeah.
Once you're ready, let's go.
Yeah. Firstly, thank you for having me and giving me this opportunity. Before to start, I want to introduce my research interest. My research interest cover from the synthesis of MS2 or TMD materials through sensory application and interaction with purely organic materials. Today, I want to focus on some TMD interaction with purely organic materials. So today's topic is chaotic organic and organic phosphorescence pattern for physical unclonable function. Here's the contents of my presentation. Let's begin with the IoT and security. IoT is a giant network with connected devices. This IoT is highly impacting on our daily life. So let's imagine that we forgot turning off air conditioner and lights in the house today morning. Then we can easily turn off them just from anywhere. So with the explosion of IoT devices, the IoT security is getting essential tool for safe IoT. So I believe that the physical unclonable function or PUF is a highly promising solution for that. Then what is PUF? PUF is a digital fingerprint of electrical devices. This can serve unique identification to authenticate and secure devices. Then let's look into each part of PUF. PUF, the first part is physical part. Physical part refers to the fact that PUF relies on the physical feature of electrical devices. So let's suppose the threshold voltage of our transistors in my phone is designed to be 1 volt. In that case, the actual distribution of threshold voltage will follow this kind of bell shape due to the manufacturer variations. So if I try to make some kind of password, I can utilize that randomness as a chip code. The second part is unclonable. Unclonable part means that entire physical feature or variation are impossible to replicate from others. Then lastly, functions. Function is actually a very critical point to connect between physical features and the authentication process. The response to each challenge will be very random, and there are thousands of challenge and response pairs. Therefore, Prof is highly secure and take low cost to generate random number and cryptographic key. So let's go over the classification of Prof. Based on the fabrication material, Prof is largely divided into two parts, silicon Prof and non-silicon Prof. And there are many methods to produce this Prof, such as Prof. However, recently many researchers have been interested in the pattern-based or image-based Prof. Here are some examples. The first one is sub-micrometer Winkle Prof. In this case, the pulse laser is irradiating on the surface of chalcogen thin film and forming sub-micrometer winkles. And second is artificial fingerprint Prof. In this case, they made up the polymer particle by the polymerization of two mixed polymers. And then the e-double and inkjet printed Prof. They are based on their emission image to produce randomness and chip code, especially inkjet printed Prof utilize the random droplet of ink itself as an anti-counterfeiting code for artificial intelligence. So, reviewing this article, I came out of one idea about chaotic pattern can be utilized for Prof. So for this work, I define the disorder purely organic crystal on the MOS2 seed as a single cell for pattern Prof and make large security label by designing shape and location of single cells. So as you can see from this emission image, I made a large-scale Songyungan University emblem labels and magnified this point. There are 100 of single cell of pattern Prof, and each cell has very unique and random pattern. For this motivation, I selected two types of purely organic material, DDT and MP6A. In the case of DDT, it consists of two hydroxyl group and carbonyl group, which induce the highly strong intermolecular interaction. And its emission property is blue fluorescence at room temperatures. In the case of MP6A MP6, there are two bromine atoms for MP6A and one bromine atom and one carbonyl group for MP6A. The mixed component of MP6A and MP6 can achieve sufficient intermolecular interaction and enhance their crystallinity as well as phosphorescence lifetime. So this MP6A MP6 emission property is ultra long lifetime red phosphorescence. Also, through the preceding observation, I confirmed that the 2D material such as MOS2 or WS2 can site-specifically control the crystallization of purely organic materials. So these images present the real-time crystallization of DDT on the MOS2 flake. And also, this MOS2 actually can tailor photophysical feature of DDT from blue fluorescence to green phosphorescence. Moreover, the MOS2 basal plane can enhance its crystallinity of MP6A MP6 via solution process and leading to the highly efficient room temperature phosphorescence like this. Based on this technique, I want to make large-scale chaotic pattern. For that, the two-step growth method is implemented to synthesize large area MOS2. At first, a few nanometer thick MO film is deposited on the substrate, and this film is fully transformed into MOS2 with H2S gas injection under high temperature. And as synthesized, the film consists of bi or tri-layer of amorphous structures with nanometer scale MOS2 grain. And these films are characterized by Raman and XPS analysis and revealing great quality and is relevant to MOS2. And the TEM image of this film shows this film contain randomly oriented small grains. Actually, this can achieve high randomness of finer purely organic crystal on the MOS2 because the purely organic material tend to nucleate and crystallize following the lattice structures of MOS2 basal plane. And based on that atomic seed, I formed the purely organic material and MOS2 heterostructures. As I mentioned earlier, MOS2 can achieve sufficient and stabilization of phosphorescence attributed to crystalline enhancement of purely organic materials. So, in peer spectra, DDT shows great redshift with MOS2, and in the case of MP6A and MP6, it also enhanced their phosphorescence part with suppressing their fluorescence part. Accordingly, in CI matrix, DDT and MP6A and MP6 alter their emission color to green and red, respectively. In addition, the time-reserved PR spectra also present. The DDT and MP6A and MP6 increase their lifetime with MOS2. This result indicates that the MOS2 actually stabilizes the phosphorescence behavior of purely organic materials at room temperatures. So, based on this technique, I formed the large-scale phosphorescence pattern for chaotic puff. As you can see from this optical image, each crystal has very random and unique. Owing to this microstructural uniqueness, we can tell apart a large-scale phosphorescence label. And also, I want to estimate the encoding capacity of each puff. So using this emission image, I classify the morphological feature of DDT and MP6A into the 5 criteria: area, aspect ratio, number of crystal, orientation, and position. Among these parameters, the orientation and position have flat distribution like this. This flat distribution can achieve and boost the encoding capacity number for one MOS2 set. In addition, the number of crystal and its probability also exponentiate this encoding capacity. Moreover, if I want to make a large-scale security label with A by B array, in the case group encoding capacity exponentially increases. Through these formula, I could estimate that the 1 millimeter scale of MP6A and MP6 MOS2 pattern can contain more than 10 to the power of 70,000 encoding capacities. And finally, 2D cross correlation is implemented to evaluate full pattern's uniqueness and randomness. And as you can see these figures, the correlation coefficient is perfectly separated each other's, which means the full pattern has no repeatable part and it has perfect randomness. I would like to recap the main point of this research. First, this chaotic pattern can be readily fabricated by solution process. And this pattern are observed by a foldable spectrometer like optical microscope or CCD camera. And based on the image analysis, we can estimate its encoding capacity and evaluate their randomness. Through this process, we understand this chaotic pattern path can be utilized as anti-counterfeiting code. So if that code stored and saved in database, finally, the authentication process can be demonstrated by the communicating user devices and database. And here's my reference in this paper. And thank you for listening. Do you have any questions?
Thanks for the nice talk, Dr. Im. And then we have just 1 minute, so let's have a quick question.
Yeah, hello.
Hello.
Yeah, Dr. Herin, do you know how do you know the orientation of organic crystals?
For other research, I want to check the STM analysis to check and measure the purely organic material between on the top of the MOS2. STM analysis can be work.
Okay, understand.
Yeah.
Thank you.
Thank you.
Okay, if there are no more questions, move on to the next invited speaker. So next invited speaker is Professor Paul Weiss. He is a nanoscientist and holds a UC presidential chair and is a distinguished professor of chemistry, bioengineering, and material science at UCLA. He studies the ultimate limits of miniaturization, developing new tools and methods for timing resolution and spectroscopic imaging and chemical patterning. He applies these advances in other areas, including neuroscience, microbiome studies, quantum information, and high-throughput cellular therapies. He has won awards in science, engineering, teaching, publishing, and communication.